Yeah, today we are going to talk about basically simple harmonic motion. Simple harmonic motion is very
Sir, you
important.
haven't shared the screen, sir.
I didn't share.
No, no, sir.
Oh, thank you. All right, now you can see that, right?
Yes, sir.
All right, so we already familiar with this keyword motion actually, because we discussed about in the linear motion, that's mean the linear kinematics, and also circular motion, and also the rotatory motion. We are familiar with that. Now, harmonic basically actually that periodic motion, that motion actually going to be the repeated itself over and over after a certain time. You have that idea for a simple pendulum. Let's say this is your simple pendulum hanging by this string with that mass. If you release that system from that side, you know that it will be oscillating in that way, right? So this makes a complete oscillation. Once you start from that point, let's say this is the point A, this is the point B, it goes to the point B, and again from B to again it goes to the point A. When it's come back to the its initial point, which means at the point A, it makes a complete oscillation actually, because it's a back and forth motion. That is known actually oscillation. And this motion will be go on, right? If you neglect the air friction actually, obviously. That's why it's a simple harmonic motion you're talking about, that keyword. We'll neglect that damping factor on the system. And this motion is going to be repeated after a certain time. That's time actually, certain time we define the time period actually. That's why it's called that harmonic motion. And simple, we are not going to include that damping factor over there. Sometime it would be the system is going to be the complex harmonic motion actually. We are not going to concern about that complex harmonic motion. We will only focus on that simple harmonic motion of the system. But idea is same. If the equation is going to be that complex, you will find out that different root actually, because this is a simply we are going to define that motion by a equation of motion. That's known actually that general equation of motion of this type of system, which is known actually, which is simply a differential equation, second order differential equation for simple harmonic motion. We are going to solve that differential equation for this system or this chapter actually. Very straightforward. Fine. To study of this one actually, basically we need to introduce some parameter. Or first one actually is a periodic motion. Periodic motion, the motion which is going to repeat itself over and over after a certain time. So it's called actually that periodic motion. You can say that example of a ticking of a clock, which is going to be that actually that periodic motion. Even though your heartbeat is also that periodic. If it is not periodic, then you need something else actually. That's called the pacemaker, right? When it's not given the periodic. Fine. So second one, we need to discuss about that time period. Time period is we define time required to make a complete oscillation. So that's mean we also discussed that thing in the rotational motion also, or the circular motion. When the system start from that point and goes around this circular path and come back its point, it's called actually that one revolution. To make this one revolution, whatever its time it takes, it's called actually the time period. And same thing for the simple pendulum. You can say that it start from that point, goes around B point, and again it come back to the A point. It makes a complete oscillation. That's why whatever the time it will take, we'll say that would be the time period actually, that we define by the T actually, or represent by the T. And third one, we have to focus on that frequency. Frequency actually number of oscillation per unit time. Number of oscillation per unit time. which means how frequently actually or how rapidly a oscillation take place. Oscillation means, again I will say that, which is at the back and forth motion, a repeated back and forth motion actually around the equilibrium position is called the oscillation. Because equilibrium point is very important for this harmonic motion actually, because you have that idea actually, if you release that system, this is actually your system which makes the angle over here, the theta, and you know that if you draw the free body diagram of this system, which I can write, this is my mg, and at that point this is actually that mg, and you can say that upward force is the T tension will be must be equal to the mg over here. That's why it's the equilibrium point. And you can take that component of this vector, this would be mg cos theta, and this would be simply that mg sin theta, right? This system is trying to move towards that this equilibrium point, which means this force mg sin theta actually doing their job. Once this come to the point at this equilibrium point, after coming to the equilibrium point, it's not going to stop because it has that inertia. Due to that inertia, again it's trying to move in that direction. So once it's come at that point, after just crossing the point, the force is actually also change its direction. It would be always towards that center, which at the equilibrium point. It's trying to keep in that state at equilibrium state. In that case, obviously, it has to do the minimum amount of work. That's why this point is known as the equilibrium point, and that oscillation takes place about this equilibrium point. And this is very important, and this is more important parameter for this harmonic motion. Oscillation must take place about the equilibrium point. All right. So we define that number of oscillation per unit time actually called the frequency, and that frequency usually expressed by the f. This is called actually linear frequency. It has a relation actually f actually 1 by t. You know that that is called actually that second inverse, right? Or that we define the unit actually that hertz actually we say that. There means one more frequency we need to concern over here. That's called actually angular frequency of the system. Angular frequency that will be expressed by that omega. Omega should be twice pi f, because we define that omega actually in terms of circular motion, we define it twice pi divided by t, right? That we know that because f actually the 1 over t. So angular velocity we define twice pi over t, which is actually that revolution or rad per second actually. Rad per second, we define that one actually. And sometimes we also say that this angular frequency also the second inverse, which is actually the hertz. That's how actually we can define that angular frequency of a system. Alright, so there are two major conditions for simple harmonic motion of a system. We are going to write down this.
So can I see the formula?
Formula for what? This one.
The frequency. Yes.
So is it radian per second or revolution per second?
Rad per second.
Done.
Alright, so the condition is, first condition is the oscillation take place about an equilibrium point. That's I already discussed to you actually for this one, because the system will be always try to move about that equilibrium point. Second one, that motion is periodic. That means it will be repeat motion after a certain interval, which is actually after a certain time period, right? These are the two major conditions for simple harmonic motion. If the time is not going to be periodic, then it would be actually that complex system actually, which is not going to be harmonic, it should be in harmonic motion actually. All right, so now we are going to define the general or we are going to derive actually that equation of motion of this system which undergoes a simple harmonic motion. Let's define with that most classical system, which we say that spring block system actually. For this case, let's say I have this spring is connected to a block actually. This spring is massless we are considering, and this surface is also the frictionless. Let's say this is the mass of the block and this is the spring constant. If you drag this one by a force, then this system is going to be extend the spring, right? I can draw that one. Say, let's say this is actually that new position, which means it's going to be extended that one, because that one actually that equilibrium point of the system. Right now, this is actually is extended, which means this is actually that x is going to be that extended of that part. Plus. Then once you release that system, it will be try to come to that equilibrium point. It will, because when you drag the system, this spring is going to be the stored its potential energy. That potential energy we can find out. We know that this elastic potential energy of the spring is simply half of kx square. It will be gained that one. So once you release that spring will try to release that potential energy, which means it will be trying to move. It will be moves towards that center equilibrium point. In that case, this potential energy will be converted to the kinetic energy of the system. Once it's come to that point, at the equilibrium point, in that case the system has a kinetic energy. That means the system has the inertia. Due to inertia, it will also try to compress the system again towards that direction. Let's say it will be come again over here when it's going to compress from equilibrium point. Let's say this is actually that x minus. Since I choose this is my origin or the equilibrium point, which means that the system will be oscillate between these 2 points, or this is, if you consider this is the O, this is the A and this is the B. The system will be oscillate back and forth about these 2 points A and B, keeping that equilibrium point at the O, right? This from the equilibrium point, that maximum displacement which is at the point A in the positive direction and also towards the negative direction which is at the point B is equal. It has to be equal if it is that frictionless actually. Obviously, it will be harmonic in that case. And that displacement we say there, that's called actually that amplitude of the system. This is called actually that amplitude, and that amplitude will be expressed by the A of the system. Now, I want to find out that position of that this block at any time.
Is that strain energy?
Strain energy means?
Sorry to interrupt. That ES equals to half kx square.
That's the elastic potential energy. Elastic potential energy.
Ah.
ES means elastic potential energy. All right. Now I'm going to try to draw that position of this particle at any time t about this equilibrium point. Let's try to draw. So that I can draw. Let's say I start from that point actually. So what I can say, it will be start from that point. Once you release, it will goes towards that equilibrium point at a certain time, and again due to inertia it will go to the negative that point, and in that case the spring is again is going to be that store that potential energy. That means that kinetic energy is going to be the potential energy again when the spring is going to compress. Again it will try to release that potential energy, which means it will be gain some kinetic energy, right, of the system. Sorry. Then it will try to move again in that direction again. So that's mean that would be basically that motion or position of the particle at any time. It will be goes on actually in that way, which means I can say this is actually the equilibrium point. From here it has some positive maxima displacement and also a negative displacement from the equilibrium point, and from the equilibrium point this distance or this distance is known as actually the amplitude of the system. We say that amplitude, amplitude of the system, and that amplitude will be expressed by the A. Fine. Now this function is familiar to us, is a general function actually, your familiar function. If I present in that way, this function is look like, let's say this is my time, this is my displacement, and it will be look like that, right? And that function actually we know that is a cosine function, cosine x, we can write down some parameter over here. This is a cosine function, right? Which means we can represent the displacement of a system which undergoes a simple harmonic motion as a cosine function actually. In some book they also represent by the sine function. In that case it will be start from that 0 actually in that way. It's the same thing, but it will be little bit different actually. But in your reference book they use actually the cosine function, so that's why we will also write down is a cosine function over here. All right. So now look at this. If I try to represent this function over here, try to understand, this is my, oh God, this is the point. Let's say this is the point 1. I'm trying to indicate this is the point 2, this is the point 3, this is the point 4, this is the point 5, which makes a complete oscillation for that one. In that case, I can say from here to here that total time is going to be basically the time period of the system, right? Because it makes a complete oscillation in between these 2 points, in between point 1 and 5, which is actually the total time. And we can say in between point this one, it should be half oscillation. That's why its time period would be t by 2, not the t by 4. It should be t by 2. And this one, this part is going to be actually that t by 4 of the time. This is actually the equilibrium point of the system. So once you release the system from your equilibrium of that point to 1, this is actually your releasing point. From here to here, when it's come over here, obviously it is actually that 1/4 of its complete oscillation. That's why its time period would be 1/4 t. And once it goes that one, the other side of the maximum, which is actually that point, and this is actually again is going to be that t by 4. So the total, this one, which is point 1 and 3, is going to be actually that t by 2. It's a half oscillation. So that's at the time period goes to the half. And from that point again is come over here, which is actually that point 4. This one is the point 4, and obviously this one should be this would be t by 2 plus t by 4 actually, which is going to be actually that 3t by 4 time period. So that's mean in that time, in that way actually we can also predict that position of the particle in terms of time period. Fine, let's try to find out initially first what should be is equation of motion, then we will also find out that other thing. To find out the equation of motion, what I'm going to do, I'm going to make the position of that. Let's say I'm going to say that since I'm going to represent that function is look like that, right? So what I'm going to do, I'm going to cut off this function from here to here, and this portion I'm going to place over here. Then it should be look like a circular motion actually. So making that analogy, I'm going to find out the displacement equation so that it would be easier for you to understand. So that's why I'm doing that. Let's say this is my axis actually. I make this circular track, semicircular, the system is rotating. Let's say at any time is reached over here, this is the point P and it's rotating about this counterclockwise direction. This is my x-axis, this is my y-axis, and let's say this is actually the position of that particle. This is my equilibrium point, or you can say the origin, and it makes a angular displacement which is actually the theta, and this is actually that amplitude, because this is from the equilibrium point, this will be the maximum displacement of that particle. And you can consider this is actually point 123, this is half cycle, not the half cycle, 1/4 cycle. This is actually that half cycle from in between that point to that point, and this is actually complete cycle. That's why we try to draw in there. Then I can draw this, the position of that point. I can also write down in terms of Cartesian coordinate. It should be x and y, right? So then I'm supposed to write this would be simply x and y coordinate, which means I can say that vertical displacement would be that y, and that displacement is going to be the x, right? So then I can form this triangle, right, and triangle. We can say this is my theta, this is my y, this is my x, and this is the a actually, which is hypotenuse. Then we can define that cos theta would be simply base, which is the x over hypotenuse a, right? Can you write that definition from the trigonometric definition? Which means that x would be a cos theta, and theta we can also define. We know that angular velocity omega actually angular displacement over time, which means that I can write down the theta would be simply omega t, or I can write down this displacement is a cos of omega t, right? And that's actually say the displacement of a particle is undergoes a simple harmonic motion. Most general way we represent that displacement actually, x is a function of t, it would be a cos of omega t plus phi. Phi actually that initial state of the particle where it is when it starts its journey actually, which is actually we say that that is the phase constant. In phase actually indicating that initial position of the particle, because in that function actually it can be start from any point. It can be I start from that point, it could be start from that point, any point on this trajectory. Phi would be that one actually. All right. Fine. So that's called actually the most general displacement.
Can you scroll up a bit?
Is it okay?
Yes, sir.
Alright, sometime we can also write down this equation also in another format actually, if you ever see that equation, so that you are not going to be surprised that, so because this omega we can write that's actually twice pi over capital T in terms of time period into this is that time small t plus phi. That is one more representation also, that displacement of this particle in that way, oscillating field actually. Alright, so we will focus on that part actually. So
I did not understand this one.
which one?
Sir, that formula that xt equals to a cos omega t plus phi, where did phi come from?
Alright, so do you understand this one, x equal to a cos of omega t?
Yes, sir.
Yeah, into
Yes.
that equation I just simply add that one, which is actually initial position. If I say that phi equal to the 0, then what we are going to get? We are going to go back to this equation again. Alright?
Yes, sir.
Yeah, phi actually that indicating that position of that particle actually, because you can find out that phi, if you say that this is that it is start from here is angle is 0, but it is start from that point, what will be the phi?
Phi will be a value.
Phi would be a value which would be the 90 degree, right? In terms of degree actually, 90 degree. If, so that's why it can be start from any point actually. I choose from this reference point, but it can be start from any point on this trajectory. Then phi would be some value actually. Phi indicating the initial position of your particle where it is going to be start its oscillation. And we say that is actually the phase constant from the system.
Sir, is phi a angle?
Of course, is a phi is the angle. For this oscillating field, obviously this is the angle over here because you are indicating that position of that particle into that function, this trajectory. It could be a degree or it could be also the radian.
Sir, so the position is indicated by the angle.
Of course. Are you surprised for that one? Then what you did in the rotational motion? Don't we present that angular position? Don't we talk about that angular position in that rotational motion?
Yes, sir.
Yeah, same thing we are doing over here. That's why I'm saying that please, you need to know that previous lecture once you follow my following lecture. So you have to know that previous topics, whatever I discussed in the previous classes. Alright, so fine. So we will express that position function of a system undergoes a simple harmonic motion. We are going to express A actually cos omega t plus phi. That's the most general way we represent that displacement of the particle. If I know the displacement, then I'll be able to find out that velocity.
Yes.
Please make you silent by yourself. Velocity would be simply dx over dt, which means
Huh? Charging time.
Arshia, your mic is on.
so dx over dt, if I take the derivative of that function, it would be simply minus a omega sine of omega t plus phi, right? Because sine would be that cosine function would be minus sine omega t, but omega is also over here is a function of t. That's mean a is constant. You know that derivative. I'm not trying to explain those parts. You're supposed to know that one. That's called actually the velocity function. And if I know that velocity, then I'll be also able to find out that acceleration of the system. So acceleration is going to be that simply dv over dt, which means I can write down this acceleration is going to be that minus a omega square cos of omega t plus phi. That should be my acceleration function at any time. We're going to find out acceleration using this. These are the major equation to understand that acceleration. Now you can also graphically represent. There is one more case actually. We can write down this acceleration equation. Yep.
Sure, we are differentiating. So, oh wait, never mind. My bad. I actually thought we were differentiating, distance. That's why I thought of, differentiating pi. Phi.
I didn't get you. Say it again.
No, I was wrong.
Okay. Can I proceed right now?
Yes, sir.
All right. So fine, A would be in that case, I will be right. It should be A omega square, or not the A omega square, because I can write so that you can write this A is going to be that simply I rearrange this equation is simply minus omega square a cos of omega t plus phi, and a cos of omega t plus phi, again that x we represent, which means I can write a would be omega square into x. That would be the acceleration of that system if it is undergoes a simple harmonic motion. These are the characteristics equation of a system, and from this equation you also will derive that general displacement equation. So how? If I know that acceleration, then I will be able to write down equation of motion of the system using the Newton's second law actually, which is or you can write down from here also. We can write down this one is going to be that a you can write down, so which is second time derivative of the position function, dx over dt would be equal to that omega square x. Then you can write down d square dt square plus omega square x equal to the 0. That's that general displacement or equation of motion of a system undergoes a simple harmonic motion. And this is known actually equation of motion for simple harmonic oscillation. If any system undergoes a simple harmonic oscillation, then the system has to satisfy this equation. And you will find out any system undergoes a simple harmonic motion, its equation of motion would be look like that. I'll show that, I'll derive that part step by step. But before that, I need to actually that graphically represent those function actually, position function, velocity function, and this acceleration function. There is some importance of this function also. Let's first draw that. This is my who is knocking right now? Alright, let's say this is my position and this is my time actually. Let's say this is my plus x, 1, 2, 3, 1, 2, 3. Let's say this is my minus x, and this is my equilibrium point. I'm going to mark that one, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, and so on. My position function was actually x actually a cos of omega t plus phi, right, which is actually the cosine function, which means it will be start from that point. So it will be start from that point, it goes toward this point, from that point, and it will move in that way, right? This is actually that cosine function, which is actually position function, or I can write this is actually that xt at any time. Fine. Now what about the velocity? Velocity function, you know that velocity actually minus a omega sine of omega t plus phi. This was the velocity function, right? Now let's try to draw that velocity function by different colors. So velocity is sine function. So we know that the sine 0 actually is 0, right? We know that one. So which means it will be start from 0, and let's try to go so the point. So the point. So it will be start from that point, sine 0 0. Goes to this point, and it will be passes through this way. This would be actually that velocity at any time t. Now interesting thing, look at this from these two curve actually. When you find your velocity actually, this is the velocity would be maximum, or that point is maximum velocity, right? That point actually maximum velocity. At that point your position actually that minimum. That's happen actually when you release actually a simple pendulum. If you're thinking about a simple pendulum case, this is actually an equilibrium point. If you release from that point, you release the system from the rest, which is start from that case, velocity is 0, that point, and once is and I know that this is actually that maximum displacement. When it's come to at that point actually your displacement is 0, but the velocity is maximum. Velocity or speed, you can say the speed, because velocity will be in term of another way. And that why it's try to move in that direction. When it's reached again that negative maximum, at that point the velocity actually that 0 over here. That's why it stop over there, momentarily stop and change its direction, and again it try to move toward that direction, which means at that point again it has negative maximum displacement. Once you start from that point, which is the positive maximum, which is this point, at that point actually the velocity is 0. Once you come over here, which is actually that equilibrium point, which means that point at t by 4, your velocity is towards that direction, which is actually the negative maximum. And when it's reached again to that point, maximum displacement, which is this point, negative that point, at that point the velocity is 0. That's why it stop over here. Again is trying to move towards the forward direction, and at that point, which is this point again, is come back over here. At that point the velocity is again positive maxima. That should be that maximum point over here. Now at that point, that again the displacement actually the minimum, and that's how actually we can find out the relation between that velocity and that position of a system undergoes a simple harmonic motion. And even though we can find out at what time that velocity will be maximum in terms of time period, because if you say at that point the velocity will be towards that negative direction, right? So that's why I will say that at that point the velocity is minimum, because its direction towards the negative direction, which is actually the time period should be t by 4. Then again when it's come over here, at that time the velocity actually the positive, then I will say that would be that maximum velocity, and that would be actually that 3 t by 4 time, because it will start from there. This is actually the t by 4, sorry, t by 2 to make a half oscillation. Again is come back over here at that equilibrium point, which is actually that t by 2 plus t by 4, which makes actually that 3 t by 4 actually would be the time period. At that time that velocity of this system is going to be that maximum. Fine. Now what about that acceleration? Acceleration actually we write down those equation, actually they are simply opposite of your position function. It was minus omega square a cos of omega t plus phi, right? Then you can write down, so it will be start from that point, negative maxima, it will goes in that way, passing through that point, and it will go in that way. So that's why it's got Spanish. Passing through this point, it will goes in that way. That should be actually that acceleration of the particle at any time, which is simply the opposite of this displacement function. You can also find out, because I write down this equation, this acceleration equation actually I write in another format. Actually you can write down, it should be a is simply minus omega square x, right? From that one I also derived that equation of motion. You can find out when x is minimum, so that's when x is negative, a will be positive. You can also find out when the x is minimum is over here, it's a negative, right? At that point a is positive, which is that point. If the x is positive, where is this point, then the acceleration would be negative, which is that point, right? This equation is also telling me that one actually. You can also find out that relation between that position, velocity, and also that acceleration in that way. And you can also find out that one more equation, which we say actually that energy, total energy of the system, you can find out simply, you can write that equation actually, total energy would be simply that kinetic energy plus that potential energy of a system. and depending on the situation, its energy is going to change, potential energy. Kinetic energy will be simply, you can write down half of mv square, and the potential energy would be different for different object. If you think about for a spring block system that I defined, that would be simply that half of kx square, right? That would be the case for this elastic potential energy for the spring block system. And we can find out that relation from here actually. So what would be the total energy for this spring block system? Before that, we can also find out this spring constant. If the system moves then in this block system, then what should be is equation of motion for the spring block system. Let's find out that one first. So then I'll find out also the total energy for this spring block system. I will also do for the your simple pendulum. Let's write down, this is going to be that spring block system. I'm going to drag it, since it's a frictionless, this is the spring constant, I'm going to drag. Then I know that the spring force is going to be the minus kx, right? Then this force I can write down, it says simply that ma from the Newton's second law, it should be that kx, right hand side. I can write down this in terms of position is going to be the d square x, dt square would be minus kx, right? Then I'm going to rearrange this equation. It look like it should be minus k by mx. Then if I take d square x over dt square plus k by mx equal to the 0. That is actually the equation of motion for this spring block system, right? Now if I consider or compare with my general equation of motion, which is I derive d square x dt square plus omega square x equal to the 0, which is the most general equation of motion of a simple harmonic system, then I can say that my omega square should be k by m for this spring block system, which is actually the angular frequency. That means we can say that angular frequency would be simply k by m, right? This is actually the angular frequency for this spring block system. If you use the different system, this angular frequency is going to, parameter is going to be different actually. Now if you know this angular frequency, then you will be able to find out that linear frequency, because linear frequency we define omega actually that twice pi f, which means that f should be simply omega divided by twice pi. Then I can write down this would be twice pi root over k by m, or I can find out the time period in that case. So the time period would be simply 1 over f, which I can write, it should be twice pi root over m by k. That is actually would be the time period for this system. So that means if I just can derive that equation of motion of the system which undergoes a simple harmonic motion, then I'll be able to find out that frequency, which is angular frequency. If I know the angular frequency, I'll be able to find out the normal frequency, which is this one f. And if I know that normal frequency, I'll be able to find out that time period of the system. Not only that, even though I can also find it, if I know the time period, I'll be also able to find out that velocity at different point. I know that in terms of time period, right? It's a t by 4 is going to be that minimum velocity, and 3t by 4 is going to be the maximum velocity of the system. And even though you can also find out the position using that one. You can also find out in another way that velocity in terms of energy, the energy for the spring block system I write down, which is actually kinetic energy, that's going to be that half of mv square plus the potential energy for a spring block system is half of kx square. If you plug in those parameters over here, so kinetic energy actually, let's write down that kinetic energy, which is half of mv square. V is you find out, which is the minus a square would be omega square sine square omega t plus phi, whereas potential energy which is u, I'm writing for the spring block system k x square, it should be a square cos square omega t plus phi, which means if I write down these two equation, what I can write, it should be simply half of m a square, and omega square I will replace by the k by m into sine square omega t plus phi, plus the potential energy would be half of k a square into cos square omega t plus phi, right? Now you can write this one, you can cancel out, you can factor out half of, from the right hand side you can factor out half of k a square, then it should be sine square omega t plus phi plus cos square omega t plus phi, which makes it actually the 1. You know that from trigonometric rules, sin square theta plus cos square theta would be the 1. Then I will find out simply the total energy of this system, which is going to be that half of k square. That should be the total energy for this spring block system if undergoes a simple harmonic motion. And from that part, we are going to extend that relation between this velocity and that position. You can write down in a left hand side, you can write down half of mv square, which is that kinetic energy plus potential energy half of kx square. That's the total energy, at it must be equal to half of k a square. A is the amplitude of the system, right, which is actually that maximum displacement from its equilibrium point. Then you can drop this half. I can also write down mv square would be k, I factor out, it should be a square minus x square. I just simply take this parameter towards the right hand side, and if I divide, it should be k by m a square minus x square into root. That's the velocity at any time, and you can write down this velocity is going to be that plus minus, there will be plus minus since I am taking that one, root over k by m, actually that omega into root over a square minus x square. That would be that velocity at any position you can find out. If you know that x, you will be able to find out the velocity at any position of that particle. Interesting thing, if you say when x is 0, when x is 0, which is actually the equilibrium point, then you will find out v should be plus minus omega a. That's called actually the maximum velocity. That's called actually that maximum velocity. And what time it will be maximum, you have that idea. It's a 3t by 4 would be the positive maximum, which will be plus omega a, and t by 4 second it should be minus omega a, right? That's how actually you will be able to find out that maximum velocity of the system if it undergoes a simple harmonic motion. Alright, let's talk about that simple pendulum, which is very familiar with you. In the simple pendulum case, we have this string with a mass. The length of this string is L and the mass is N. If you track that position or makes an angle, this theta, that theta is very small, right? This theta will be very small. We know that from that our previous idea. To make this oscillation, we keep that angle should be below the 4 degree actually. It has to be that minimum. So if you draw that free body diagram of that system, I can say this is actually my mg, this would be my mg cos theta, this would be my mg sin theta. I choose this is my positive x and this is my positive y. This mg sin theta actually making that oscillation of this system, and I also know that that displacement from here to here actually that x, right? Then I can say the force actually involving to oscillate that system, actually this force is simply minus mg sin theta. that's the force actually play the role to make that oscillator of the system or simple pendulum. On the left hand side, I'll replace F equal to by ma, it should be minus mg sin theta. Then I can neglect this m, which means the acceleration would be simply minus z sin theta for this case. And now this angle, I know this is a very small actually, it's called actually small angle approximation. If you draw this angle, because I know that distance is also the x, so if I draw this right angle over here, this is actually your theta, this is actually your L, this is also L, and this is actually your x, right? If the angle is very small, this sin theta is going to be that actually that x by L, right? From the trigonometric definition you can find out, and this must be also equal to the theta. This is called actually the small angle approximation. You know that idea, you have that idea. If the angle is very small, then the ratio of the sin theta, tan theta are equal. So we will use that idea over here. Then we can write down this g sin theta, I will replace by this one, this x by L. Then we can write down this a in term of position, d square over dt square would be equal to minus g by L into x. Now we can rearrange this equation. If I rearrange, I will find out it would be d square x dt square plus gl into x equal to the 0. That is actually that equation of motion for simple pendulum. Now if you compare this one with your general displacement equation of motion for this simple harmonic case, d square dt square plus omega square x equal to the 0, if I compare, then I will find out this omega square would be g by L, right, which is the angular frequency for this part, which means that omega should be simply root over g by L. And if I know the omega, I will be able to find out f. F it is simply omega over twice pi. This would be omega divided by twice pi, which means this frequency would be 1 over twice pi root over g by L. That should be actually angular frequency. That should be the normal frequency. If you know the normal frequency, then you will be able to find out the time period, which is t would be simply 1 over f, which would be twice pi root over L by g. That's the equation you use for simple pendulum, right? Which means if you can simply derive that equation of motion of this case or any system, you'll be find out that angular frequency and also the time period of the system using that, comparing that system. That's the general procedure to find out that part. Alright, let's talk about one more case actually, which is actually you did in your lab. That's called actually that compound pendulum, or we say that is actually the physical pendulum. Physical pendulum means if you oscillate any system about this any point, that if it undergoes a simple harmonic motion, that we say that physical pendulum. In the physical pendulum, what happened, you have that a bar right, that bar is going to be the rotate about this point. This is actually this rotational point. But what happened, I know this mass of the system is going to be that at this point, this is mg, and you can say in that case this is would be, if you say this is actually that angle, the theta is going to be created over here, then I can say this is actually that mg cos theta, and this is going to be that part which should be mg sin theta, right? But what happened is going to create a torque over here, because this is actually the distance, the t, that's the whole actually you measure that length. Actually you take that different point oscillation, but we are going to find out for one point that oscillation. For this one, since it's going to create a torque, I will use the Newton's second law in terms of rotational case actually right now. That would be torque should be that I alpha, which is analogous to the F equal to ma, right? This torque could be find out because we know the torque actually R cross F, which is going to be that minus mg sine theta into d equal to I alpha, right? Torque I calculated because I know that this is my d, this is my force, which makes the angle this 90 degree, and from the torque equation I know that torque tau should be R cross F. R is d over here and F is mg sine theta, and it is towards the negative direction, so that's why I give you the minus sign over here. Fine. Or you can say that it's moving to the clockwise direction due to that torque. That's why you say the minus sign. That's more appropriate actually for this torque, because obviously it's going to rotate. Due to that force, it's going to rotate to the clockwise direction, not in the counterclockwise direction. That's why it's a negative sign. Fine. Then I can also write down this one in terms of phase. This is mg theta, mg d theta. For the same case, the small angle approximation, we will write down instead of sine theta, it should be simply the theta, it should be I, and alpha, it should be minus sign over here. Alpha should be d squared theta divided by dt square, right? Rate of change of angular position will give you that angular acceleration, second time derivative of that one. Then I can rearrange this equation, d square theta dt square equal to minus mgd divided by I into that theta. Now you can rearrange and compare this equation with your standard equation of motion, d square theta dt square plus mgd into I over I into theta equal to the 0. That's actually the equation of motion for this compound pendulum. And if I again compare with my standard equation, I'll find out this d square dt square plus omega square x equal to the 0. I'll find out my omega square would be simply mgd over I, where I is the moment of inertia throughout the rotational axis. For this rod, this one you can find out, this I should be obviously I should be I's center of mass plus md square. I have to use that parallel axis theorem because that the moment of inertia is going to be that throughout, it is oscillating about this point, right? About this is actually rotational axis for this case. This is that rotational axis. Then obviously I have to find out the moment of inertia throughout that point. That I can find out throughout the center of mass actually, because it is, this is the center of mass, it is the parallel with that axis, so that's why I can find out using the parallel axis theorem. I can find out that one. Then you can also find out this angular frequency is going to be that mgd divided by I, that must be actually that twice pi f. Then you can say that f should be simply omega divided by twice pi, which means it should be 1 over twice pi root over mgd over I. That would be the normal frequency, and time period would be simply inverse of that. Of this part is going to be twice pi root over I divided by mgd. That should be the time period equation for this compound pendulum. And this is the equation probably you use in your lab. Alright, so that's how actually, if you can simply find out that equation of motion,
Please roll up a bit.
if you simply can find out that equation of motion of that system, you'll be able to find out that angular frequency as well as the normal frequency as also the time period. That's how actually we will create that part.
Sir, can you scroll up a bit more?
Sir, is this d the distance of the center of mass?
Yes, center of mass to the new rotational axis. Alright, that's all for this chapter
So it's
actually.
done.
Okay, thank you very much. So I'll do some problem actually, because time is over for today actually. I'm going to do some problem and I will upload it into actually the YouTube channel, or I'll also do some problem in the next class. Alright, that should be also the last class for you.